Welcome, St. Andrews students. We're going to do an online lecture, and so that we'll have more class time for other more interesting work. The lecture is a really brief history of physics. Anybody who's watching this that was expecting something else should probably stop watching, I don't know, now. Now would be good. So for the rest of us, I want to talk about why we're doing this. We're doing this because the history of physics is, in many ways, as important as the physics itself, even to the physicists, not just to the humanities people who really automatically care about history. Partly because it's going to help you understand why we do physics the way we do in the modern world, and partly just so you have a context of where this kind of intellectual investigation came from. So the way we're going to outline our really, really brief history is by leaving most events and people out, but we are going to focus on a few people who have such tremendous colossal historical importance that we have to include them. So before we move on to the people, let's do a quick definition of what is physics. What is physics? Physics is the study of physical things. Not much more you can say about that. In particular, in physics, we try to study really basic laws of nature about things like motion, forces, sound, light, and energy. The more complicated sciences like chemistry and biology deal with lots of things all put together and all happening at the same time. But in physics, we try to isolate just one variable at a time or one phenomenon at a time. It's still a lot of fun, even if it's a little less complicated than the other sciences. By the way, if you haven't already opened up the PowerPoint at home, please go ahead and do that now. And please, before continuing, print out a sort of note version of the PowerPoint slide. Maybe your instructor already handed you a note version, fine, whatever. Make sure you have a printed out copy of the note version of this PowerPoint presentation with the little miniatures of the slides to one side, and then space over to the right where you can fill in your own notes. Because from time to time I'm going to ask you to write some notes, and for a homework grade we're probably going to check, did you write your own sort of little unique items, insights, jokes about my hairstyle, whatever, while you were going through this. So for your homework grade, take notes while you're watching this. It'll help you have more interest in the material, it'll help give you something to study, and at the very least, it'll give you a homework grade. Oh, and as always, copying homework is not okay. Thank you. All right, the first individual we're going to talk about is Aristotle. Here's his dates. BCE, before the Common Era, is a slightly more PC way of saying BC. In a minute, you're going to see some dates with CE, which a lot of people would call AD. So BC, AD, BCE, CE, whatever. So Aristotle is 3 or 4 centuries before Christ, and he's Greek. He's a philosopher. You know what philosophers do, right? They talk, and they use language, and they talk some more. He used logic and language even when discussing the physical world. He didn't do experiments. He didn't use math. The Greeks were extremely skilled at geometry and, of course, arithmetic. But he didn't use any math or any experiments. He would occasionally talk about common sense observations or everyday phenomena that you could see. But that's about as empirical as he got. Oh, here's your first note. Off to the side, let's put a definition of what empirical means. Empirical means based on real-world evidence. Based on real-world evidence. That could be experiments, that could be careful observations of things that weren't experiments but just happened, but it is about data and facts rather than assumptions and arguments and words, beliefs. So Aristotle was great at logic, great at language, but he wasn't very empirical. One result of that is that he could draw conclusions that sounded very convincing to him or his audience, like there was a long, complicated argument about bones and constitution and manly character that ended up proving that women have fewer teeth than men. Aristotle, nor any educated person for almost 2,000 years after Aristotle, would not have dreamed of testing that by going out and counting people's teeth. That doesn't make them stupid, that doesn't make them crazy, it does make them non-empirical. They weren't interested in experimental or real-world verification of their conclusions. They were satisfied that they started in a reasonable place and finished in a place that felt reasonable to them, using what felt like good logic to them. So the claim that women have fewer teeth than men, we know it's not true. He could have found it's not true by picking a dozen or 2 dozen women and a dozen or 2 dozen men and counting their teeth and even taking an average, even in the pre-dentistry days when not everybody had all their teeth. But he wasn't interested. He didn't want to do that. That isn't how he worked. But he's super important for the following reason. He was widely regarded for centuries, and he had a compelling, satisfying theory, or really 2 theories, about how motion works. He had a theory of heavenly motion, where things up in the heavens, planets, stars, the sun, things in the heavens naturally go in circles, and they naturally go on forever at constant speeds. Sometimes violent actions happen between gods, and maybe a comet goes across the sky, or a meteor falls to Earth, but in general, natural motion is circular and forever, and violent motion may happen for a while, but after the violence ends, the motion ends shortly thereafter. It's reasonable, it's logical, it agrees with common sense. That was his theory of heavenly motion. He also had a natural and violent theory of earthly motion, meaning things on Earth, not the Earth. His theory of earthly motion was that natural motion was in straight lines and will soon come to a halt, and violent motion is anything else. If a man or a god picked up a rock and threw it at somebody else, well, naturally that rock is going to fall to the earth, come to a halt in a short period of time. After the violence ends, the motion will end shortly thereafter. A reasonable position to take. It agrees with pretty much all common sense and observation. So there's Aristotle's physics about natural and violent motion, both in the earth, on the earth and in the heavens. Okay, we're up about 4 or 4.5 or 5 centuries now to a dude named Ptolemy. He spoke Greek, maybe his first language, probably his first language. Certainly he was very competent in Greek and wrote educated things in Greek. He lived in Roman-controlled Egypt. We don't know for sure whether he was ethnically Egyptian. He probably didn't look a whole lot like that if he's lived his whole life in Egypt. But when this picture got painted, that's how you would paint wise men, and so that's what he looks like. He looks like a white guy with a beard, just like all the other wise men that this kind of painters were painting. This, by the way, is not a cross. Roman Empire at this time, not super duper Christian. I don't know the exact details, go ask a Latin student, but this is not a cross. This is a measuring staff that you would use to calculate angles and make careful star or planet observations. He imagined that the Earth was at the center of the universe, same as Aristotle did. He imagined natural motion and violent motion, same as Aristotle did. He's building on Aristotle's theories. But he takes careful observations of his own, and he has access to centuries of Egyptian data about the motion of the planets and the sun. After all, the sun god Ra, one of the Egyptian gods, one of the biggies, they kept track of things like that. It was important to them. So he had access to centuries of Egyptian data. And so from his own observations of that old data, he would put together patterns and charts and details about exactly where everything should be in the sky when. He tried to figure out a method for predicting it forward into the future, and he came up with a method for predicting things pretty well. Eclipses, most notably and obviously to the general public, were things that he could tell you about when, within a few days, and about where on the Earth you could see them. He could predict these years, maybe even decades in advance within a couple of weeks. And that's pretty cool. That says to people in his time that his model of the universe, his understanding of the universe, the things he says the universe is made of and or does, seems to be pretty accurate. I'm going to focus on eclipses for several of the people that we're going to talk about in this, and you can write this down in your notes, mostly because while that wasn't the only thing that astronomers or physicists would talk about, it was one of the biggies, and it got them fame and notice. And lots of superstitious, ill-educated people would be really freaked out if the sun disappears for half an hour. And so you could be politically powerful if you could predict when that was going to happen. You could be religiously powerful if you could say why that was going to happen. Oh, the gods are displeased with us. We must all vote for. So being able to predict eclipses is not the only way to judge who's got good astronomy, but it's one way. So that's why we're going to talk about it in this slideshow. He has trouble explaining retrograde motion. I'll tell you real briefly what retrograde motion is. Some of the planets, most famously Mars, most dramatically Mars, seem to go forwards in the sky for a few months, and then backwards in the sky for a few months, and then forwards again for the rest of the year. Really wacky. Doesn't sound like it agrees with Aristotle's natural motion of things going in smooth circles at a constant speed forever. So retrograde motion of the planets, I'm pretty sure it's Venus and Mars, but most spectacularly Mars. Mercury, real hard to see, but sometimes might do the same thing. What else do you need to know about Ptolemy? So his model of the universe is pretty complicated looking. I want y'all to imagine a little gear running around in circles on the inside of a bicycle wheel, and maybe attach another gear to the edge of one of those, to the edge of that little gear, and so the planet would be like on the edge of that second little gear. And so things are going around in circles around what? The sun, the earth, which is it? Which is it? The earth. He's imagining the earth at the center. Things would go in circles around the earth, but the circles were offset from the center of the earth a little bit for some reason, and there were gears within gears and wheels within wheels, and so it was going kind of weird little wobbly patterns all the time. Hard to put all that into a system of mathematics, particularly one that doesn't have algebra yet, but he did it. He invented a way to do the calculations to make predictions that were fairly accurate. Complicated and silly sounding, maybe, to have things going around in circles inside of circles. I don't think they thought the gears really existed, but that was their model of how it worked. So he has an okay model of the universe, the best one there is, and it's reasonably accurate, and it stands for 168 to 1473. That's like what, 1,200 years? Nobody in Europe or the Middle East or China has a better model for 1,200 years than Ptolemy's model. And I don't know a whole lot about Western Hemisphere early history and astronomy, so I just won't talk about it at all.